Okay, so again, another modeling question. First thing, define the function, put it in my CAS, and just see what I need. Yeah, so if we put that into our CAS, again, we can see that I've just defined the function as nicely as I can. I think it's really important, if you can, in the defining, just put your domain in, because then everything's restricted to appropriate values, especially with trig functions, because we know the solutions to trig functions are infinite. So if we restrict that domain, it gives us, concise answers. All right, so we've worked through, we've got our function defined, where t is the time in hours after 5 a.m. So let's go. T is in temperature Celsius. For the remaining 6 hours of the 24-hour period, the temperature remains constant. Okay, so at 8 a.m. means at t equal to 3. And if t is equal to 3, f1 of 3 is 33 on 2, which is 15.5. No, it's not. 16. It's bad. 16.5 degrees centigrade is my temperature. At what times of the day is the temperature 20 degrees? So in other words, we're solving T equal to, T of T, the temperature equal to. When is the temperature? I'm looking to find a time. So I need to solve, and you can see it on the CAS there, 20 equal to T of T. And that gives me a couple of times, 6.59 and 11.40. What are we, hours? We are in hours. So 6.59 hours or 11.40 hours. So it actually says to the nearest minute. So 0.59 or 0.6 of an hour. So it's going to be 6 hours, well, it's, as a time, it's going to be 6:36 now. Well, the time is 6 hours 36 minutes. Good question, really, because now we've got to say, well, what time is that? Well, since it's from t equal to 5, 6 hours and 36 minutes later makes my time 11:36 a.m., doesn't it? And 11 hours, 11.4 is going to be 11 hours 24 minutes. So 11 hours after 5 a.m., it's almost 12 hours, which would make it 5 p.m. So it's going to be 4:24 p.m. So that's when my temperature will be 20 degrees. All right. Find dt. So let's find the derivative of that function. So I put that into the function and we can see an answer in there. But remember, the derivative is k times. So we get -3 times pi on 9 sine pi t on 9. The constant is 0, but the derivative of cos is negative sine. So I get a positive there. So that simplifies to pi on 3 sine pi t on 9, which is what we've got over here in our calculator printout. But just notice they've given us the domain that we've defined the function for. So they tack that on the end and say, well, that derivative only applies for that domain because that's what that function is defined for. What is the rate of change of temperature at the times found in part B? So the rate of change is my gradient. So what is the rate of change at, or t equal to 6.59 and t equal to 11.41, if you like. Respectively, we substitute that into our derivative. You can see that 0.7 to 2 decimal places, positive 0.78 degrees per hour, and negative 0.78 degrees per hour. So warming up at 3/4 of a degrees per hour, and negative cooling down. Yeah. So keep in context what the question's asking you about. Righto.